If you were to ask me what is the most important thing that a student should know when you walk out of this course, I would tell you that is to be able to do a nodal or mesh analysis procedure for a basic linear circuit. And when I say basic, I'm talking up to four unknowns. Anything beyond that, you start getting into the area of computer design and things of that sort, or using the computer to solve problems for you. But being able to do a nodal or mesh procedure for a full unknown problem is really important. And if we're dealing with nodal analysis, we're looking at 5 nodes, 4 unknown. If we're dealing with mesh, we're dealing with 4 meshes. I think that's the essence of this course. The course title is circuit analysis, and knowing the two main analytical methods for solving circuit is important. So what I typically do in the class as we approach the end of the course, before final exam, I like to give students one final quiz to kind of get them ready, to make sure that I tidy up everything, that I communicate well enough that these methods are the central method, the central part of the course, and they need to know that. So we typically do a quiz. And the quiz essentially give one circuit and ask them to solve it using nodal, and then solve the same circuit using mesh. And of course, if you solve them correctly, you should get the same answer. So we're going to practice that in this lecture. I actually reach back to a past quiz and just pick a quiz that I had assigned to students. Typically, they provide about 40 to 45 minutes. In my own estimation, 20 minutes is plenty to set up the problem. I expect them to use a calculator to solve the matrix solution, so not doing it by hand. But 20 minutes is more than enough if you know the procedure to carry out a mesh and then a nodal after that, or vice versa. So we're going to reach back to a bag of old quiz and then show you the example that we're going to do today. So let's go at it right there. So this is the example of interest today. So what I want to do, I want to discuss a little bit of that example, and then we're going to go onto the document camera, and I want to set it up. I want to set it up using nodal first and using mesh after, side by side, so that student can see how the two methods really are dual and map nicely to each other. So that's what's on our plate today. And I think that's a good way to wrap up the semester. Of course, what's left is power. But as you know, power is an overlay on mesh and nodal. We have to do mesh and nodal before we can answer most of the power questions. So this is a very appropriate segment and mini lecture that we'll be doing this today. So this is the circuit here. This is a fairly robust, fairly sophisticated, fairly complicated circuit for this course. And this is the kind of expectation that if you walk out here, you can do this. We're going to solve the circuit using nodal, and then we're going to solve it again using mesh, hopefully side by side, for you to see how this method, the way I solve it is the way I expect you to solve them, essentially, both in the quiz and obviously in your final exam. It suffices to say that you should expect questions on mesh and nodal in your final exam as well. We're dealing with a steady state. You know this, a steady state circuit, because I'm asking you to use the phasor method. The only way the phasor method works is for steady state sinusoidal AC circuits, if you will. Okay, so this is a circuit in steady state. What does that mean? That means the sources have been on for a long time, and we look at only the force part, the particular part of the response. This problem is asking to calculate IA, but it wants you to calculate the node voltages using nodal analysis, and in mesh, the mesh currents, and then IA in the time domain. So 10 points for each method, obviously, so that's not it. So what are the typical things we need to think about here? When we're using phasors, once we determine that the circuit is appropriate for phasors, that last part of the course, essentially, we're only looking at phasor circuit, AC circuits. Then you need to look at the sources and see their frequency. That's the important part here. Particularly if you have more than one sources, do you have a single frequency? As you know from the previous mini lecture, if you have more than one frequency, you must use superposition to solve the circuit. What is the frequency of each source? We have two sources here. We have a current source and a voltage source. I'm talking independent sources. We also have a dependent source, but the dependent source don't put out frequencies. The independent sources are both having 2 radians per second. Okay, we need that frequency, and we need only one frequency in the circuit because we're going to go ahead and calculate the impedance for the inductors and for the capacitors. This particular circuit has only one inductor and one capacitor. So identifying the radial frequency, in this case 2 radians per second, is important. Then I'm going to go ahead essentially and convert the circuit to phasor form. What does that mean? That means you convert each independent sources to its phasor representation. That means you essentially pick up the magnitude and the phase. In the case for Vs, it's going to be 30 at an angle 0 because the cosine 2t doesn't have a phase. In the case of the current, it's going to be magnitude 3 at an angle minus 35. If you were to have a sine function, we do not here, you would need to first convert the sine to a cosine before you go into the phasor domain. So that's converting the sources to the phasor domain. And then you calculate the impedance for each capacitor and then for each inductor. For the inductor, for L1, for example, it's a 1 Henry inductor. So it's J times omega, which is 2 times 1. So it's going to be J2 for the impedance for that inductor. For the C1 capacitor, it has a capacitance of 0.1 farad. So it's going to be 1 divided by J, omega, which is 2, and then the capacitance, which is 0.1, and that should give you minus J5. So that's what we have here. And then I'm going to have some more pertinent discussion about nodal and mesh as we solve the problem once we go to the document camera. So let's now go to the document camera. So again, I've basically drawn the same circuit twice because I want to do it using nodal on one side and mesh, and I want you to see how that plays out. In essence, how that plays out side by side. Okay, so you can see what I was talking about here, converting the sources to their phasor representation here, and then also calculating the impedance for the inductor and the capacitor. The resistor remain the same. The other thing that we do, we tend to use capital letter to indicate the phasor form of the circuit, and we'll use, if we remember, lowercase letter to indicate the time domain, because remember, the phasor is slightly a different problem than what the original problem is. Okay, so we are going to try to do our best here to use this space very efficiently to come up with essentially the nodal procedure, and then we'll do the same thing in mesh. So what is the first thing we do when we solve a nodal problem? We first find the nodes. Okay, I'm going to make them nice and small so that they don't overwhelm the circuit. I'm already having space issues here. And of course, that node here is a pretty spread out node, right? That node here is, so I'm putting nice dot, but you get the point here. Anytime you can go on a wire without touching an element, you still have the same node here. So, and I'm going to label them. V1, of course, I'm going to choose a reference node. I'm going to choose this one as a reference node. So I'm going to label the order node, V1, V2, V3, and V4. Okay. So I've identified the nodes, I've selected a reference node, and then I label the remaining nodes. Then I'm going to put current on my passive elements that don't have current on them. Okay, so we can look at here, let's say I1, I2, and the direction of this current is totally arbitrary. I4, and of course IA is already under 4 ohms, so there is no need to add another current. You know, you're just making things more complicated than they are. Okay, so that's the other preparation. The last step we do in terms of preparation, we essentially draw supernode about the voltage sources. Okay, so there is a and then this is a voltage source. It's a dependent voltage source. That depends on the current, but it's a voltage source by virtue of the plus minus that's in the diamond symbol. Okay, so we draw the supernode here. Of course, later on we're going to discuss when do we do KCL about the supernode, when do we do not at this point. Okay, but the circuit is prepared for solution. So when you're doing nodal analysis, the thing that you have to pay attention to is voltage sources. Okay, we write one source equation for each voltage source. The reason essentially because what the voltage source does is maintaining a potential difference between two nodes. So we essentially writing an equation that says what the voltage source does. Okay, so if you have two voltage sources, you have two source equations. So I'm going to write my source equations. Okay, first one here for this source here, it's simply V4 equal 30. That equation actually is done. I don't have to do anything with it. Okay, and then for the dependent source here, where the plus is, which is V3 minus V2 equal to IA. Let's call this equation, well, let's call it 2, this equation 1. Okay. Okay. So that equation is not done. That's why I'm not boxing in yet, because we still have to express IA in terms of the node voltages, basically. Okay. These are my source equations. They're actually the easiest equations to write. How many unknowns we have in this problem? We have 5 nodes. We have 4 unknown, which is the number of nodes minus 1, because one node is the reference node that we picked. Okay. So we need 4 equations. These are the first 2. They're the easiest equation you can write. The next thing I'm going to do, I'm going to look at where do I do KCL. I've written the source equations. So V1 is what I call affectionately a regular node. What I call a regular node, that's a node that's not the reference node and is not connected to a voltage source. So I can do a KCL about V1. So we do KCL about V1 here. We get I1 plus 3 at an angle minus 35 is equal to I3. And that's equation 3. Okay. Finally, the last equation is going to come by doing a KCL about this supernode here, because that supernode is a supernode that does not contain the reference node. This supernode has the reference node. We don't do KCL about supernode that has the reference node. So we're going to do KCL at the supernode, and I can call it supernode V2, V3, just to identify, to differentiate from the top. So what do we have here? Current coming in equal current coming out. What's coming in? I can see I3 coming in. I can see IA coming in. Okay, what else is I can see I2 coming in. Okay, and that's equal to I4 plus 3 at an angle minus 35. Okay, and that is equation number 4. So these are my 4 basic equations for my node voltages that I need to calculate. Okay, 2 coming from the source, 1 source equation per voltage source. So that's 2. And then KCL at the regular node V1 and KCL at the super node that doesn't have the reference node. Okay. And then now I'm going to write the voltage current relations. What that do for me, that essentially allow me to go from current to node voltages. So I'm going to go do I1 V4 minus V1 over 2, I2, V4 minus V3 over J2, I3, V1 minus V2 over 1, I4 is V3 over minus J5, I5, no, I'm sorry, IA, have I5, IA is minus V3 over 4. make sure I have all my currents here. I think I do. So now I take all of these currents here and essentially bring them into equation 2, 3, and 4. And then I'm going to collect terms. And when you're doing an analysis, you often have to put under the same denominator. That creates a level of algebraic work that, for example, you won't see in mesh. Okay. But that's the kind of things we do. So now into the KCL equations and also the source equations to get this. Okay. So what do we have here? Let's look at equation 2. V3 minus V2 equal 2IA equal minus 2V3 over 4. Okay. So, and I can multiply essentially by, so that's really, I can multiply by 4, or that's really, could multiply by 2 really. So it is 2V3 minus 2V2 equal minus V3. Okay. And then sending V3 on the other side, we get what? We get 3V3 minus 2V2 equals 0. So that's a complete equation right there. Okay. That's equation number 2. Okay. With IA being replaced by its voltage current relationship to express it in terms of the node voltages. So equation 3, excuse me, I1, V4 minus V1 over 2, plus 3 at an angle minus 35, equal I3, V1 minus V2. I can multiply the whole thing by 2, so what do we get? We get V4 minus V1 plus 6 at an angle minus 35 degrees equal 2V1 minus 2V2. Okay. So what do we have here when we collect term? We leave the 6 at an angle minus 35 on one side, and we send everybody else on the other side. We get 3V1 minus 2V2 minus V4 equals 6 at an angle minus 35. Okay. Again, forgive me if I'm doing it on the fly, so forgive me if I make some errors, so I apologize for that. Yeah, so, and then finally equation 4, which is I3, V1 minus V2 plus IA minus V3 over 4 plus I2 V4 minus V3 over J2. Plus I2, V4 minus V2 over J2 equal I4. So let me make sure I got this. So I3, make sure I didn't confuse myself, V1 minus V2 plus IA minus plus I2, V4 minus V3 over J2 equal I4, V3 over minus J5 plus 3 at an angle minus 35 degrees. Okay. And here I can multiply by J20 just to get rid of the denominator. J20 is actually a pretty good number here. So that gives me J20 V1 minus J20 V2 minus J5 V3 plus 10 V4 minus 10 V3 equal minus 4 V3 plus J60 at an angle minus 35 degrees. Okay. So I can send the minus 4 V3 on the other side here, collect terms. So what do we have? Let me just be careful here to make sure I got my stuff. So I get J20 V1. Do I have V2? Okay, minus J20 V2. And how many V3 I got? So this is going to come plus. So we get plus, let's say plus V3. And it's going to be, so it's going to be minus 6 minus J5, okay? And then plus 10V4. And what I can do with the J, I can replace the J. I can convert the J to its polar form, and it's going to be 1 at an angle 90. So what that's going to give me? That's going to give me 60, and 90 minus 35. Okay, so that's going to be 55 degrees. Okay. Okay. So that is my my four equations, four unknown really. So what I need to do after that, I could put them in a matrix form essentially and solve for them. Solve for V1, V2, V3. Okay. And I'll show you the example in a little bit here. So, and then once I get that, then I can solve for IA. Really, IA is essentially minus V3 over 4, so I can find IA of T. Okay. So I'm going to pause now to just look at these results. Hang on a second. So I went into my calculator and calculated this node voltages, and from the node voltages then, from essentially, particularly V3, I can take V3 divided by minus 4, and I get essentially IA in phasor, and then I get IA in the time domain. That concludes my problem here using nodal analysis. I wanted to do this. Normally I would write the matrix here, obviously, to show you how it is, but I don't have enough room to do. I do want the side by side so that you see how this method kind of map out one versus the other for the same problem here. So now we're going to basically do the mesh analysis part here. So in Nodal here, we look at nodes and then node voltages. In mesh, I'm going to look at mesh currents. I'm going to say mesh I1, mesh I2, mesh I3. And of course, I can call this mesh IA because that is the same current here. IA is the current on the 4 ohm, and having this mesh current, that also matches that. Okay, so those are my mesh currents here. The next thing I do, I'm going to put voltages on my passive element. V1, V2, V3, V4, V5. Okay. So this is how we prepare the circuit for a mesh analysis solution, essentially. So in Nodal, we pay attention to voltage sources. We write source equation for voltage sources. In mesh, we pay attention to current sources. So in mesh, we have to do two things. We have to first identify the current sources, and then we have to look where the current source is. Okay. In this particular case, I have one current source. Okay. When you have a current source, you immediately can write a source equation, one per current source. We only have one current source here. This is not a current source again. It's a dependent voltage source that depends on current, but it is not a current source. In this particular case here, I'm going to write the source equation for this current source. That is I3 minus I2 equal 3 at an angle minus 35. That equation actually is done. It's expressed in terms of the mesh current, so I don't have to do anything. So I can actually box it and call it equation 1. Okay. Right. That's an easiest equation to write. The next thing, essentially, I have to note that this current source is between two meshes, mesh I2 and mesh I3. This is the case where we're going to need to do a KVL about the super mesh between mesh I3 and mesh I2. Okay. But before we do that here, we have some what I would call regular meshes. What do I call regular mesh? A mesh without current source. Mesh I1 is a mesh without a current source, if you look around. Mesh IA is a mesh without a current source. So we have two regular mesh. So let's do KVL about them. So what do we have here? Minus V3 plus 30 plus V4 equals 0. Let's call this equation 2. Okay. Similarly, we can do a KVL in mesh IA. So what do we have here? We get minus V4 plus V5 equals 0. We're going to call that equation 3. Okay. Now we're going to do the KVL about what we call the super mesh. The super mesh, because this current source is between mesh I2 and mesh I3, what we do a KVL around the mesh, the perimeter of these two meshes that doesn't include the current source in them. Okay, so we're going to do KVL in super mesh, and I'm going to call super mesh I2, I3. So what is it essentially? Minus V1 plus V3 plus 2IA minus V2 equals 0, equation 4. Okay, so we get minus V1 plus V3 plus 2IA minus V2 equals 0. That's equation 4. These are our base equations. They come from the source equation for the current source in mesh. Okay. KVL in regular meshes, that is meshes with no current source, mesh I1 and mesh IA are those, no current source in them. And then we do a KVL about the super mesh. So the reason we do KVL about, we have to do a super mesh KVL for the current source because we don't know the voltage across the current source. What we know is that that current source is forcing that current on that branch to be 3 at an angle minus 35 degrees. So we write that equation, that's the current, that's the source equation we write, because that's what the current source does. Just like a voltage source forces a voltage across two nodes, the current source forces a current essentially on that branch. And so we write it because I3 is going the same direction as the current source, and I2 is opposing it the way I drew these currents. Okay, so that's the first thing here. And then now, VI relations. You can see the parallel that I'm drawing here. So VI relation, what VI relation does, it allows us to write the voltages in terms of the mesh currents, which are the unknown. So V1, where is V1 here? Again, you have to pay attention to the passive sign convention. So V1 is minus 2I3. Okay, V2 is minus I2. Okay. V3, J2 times I3 minus I1. So anytime you have elements that are between two meshes, you have to make sure you have both contribution, and then you have to pay attention to the passive sign convention. That's why you have I3 minus I1 here for V3. V4 is minus J5 times I1 minus IA. V5 is 4IA. Okay. So these are my voltage current relationship expressing the voltage in terms of the mesh currents that are unknown. Obviously, now I'm going to put them in equation 2, 3, and 4. Equation 1 really is a done equation. So equation 2 becomes minus V3 minus J2I3 plus J2I1 plus 30 plus V4 minus J5I1 plus J5IA equals 0. I can send the 30 on the other side and then collect term here. So what do we have? What do I have for I1? I have I1, so I have I1 here times minus J3. I don't have any I2 here, so I have I3. I only have one I3, so minus J2, I3. And then I have plus J5, IA equal minus 30. Okay. If I did my math correctly, that's my second equation here. You can see how this is mapping. it's a lot easier to bring in the voltage current relations into the KVL because you don't have to put them in the same denominator. So there is a bit of algebra that facilitate mesh, if you will, as compared to nodal. Equation 3 minus V4 J5I1 minus J5IA plus V5 plus 4IA equals 0. So that's what we have here. We have J5I1 plus IA times 4 minus J5 equals 0. That's equation 3. And finally, equation 4, right there, minus V1, so 2I3 plus V3 plus J2 I3 minus J2 I1 plus 2IA minus V2 equals 0. So collecting term here, minus J2 I1. Do we have any I2? Yes, we do. Plus I2. Do we have any I3? Yes, we do. Plus I3 times 2 plus J2 plus 2IA equals 0. This is my fourth equation for my 4 unknown. Okay. Again, normally I would cast them into a matrix form and show you the solution after that. If I do that, I'm just going to run out of that space and I won't be able to write the solution just like I did here. So I want to do that. I'm going to write I1, I2, I3, IA, and then IA as a function of time. Okay. So I'm going to go ahead here. And I did plug that if I did correctly here. So I1 is 678 at an angle minus 177.07 degrees. I2 is 588 at an angle minus 121.18. I3 is 678 minus 94.98 degrees, and IA is 529, 144.27. And you can see the comparison essentially in how this thing, if you did things correctly, then you end up getting the correct solution for these examples here. So I think I'm hoping this provides you not just a comparison, but it also shows you the kind of how I want to see your work described and essentially, and obviously comparing mesh to nodal. And I think this is an excellent example for you to consume. Thank you.